The factor theorem tells us that finding the roots of a polynomial function involves factoring into linear factors. In this discussion, we study some algebraic methods that help us find the real roots of a polynomial and thereby factor the polynomial. We begin this with rational zeros theorem. It states that given p of x with the integer coefficients, let p over q a rational number where p and q have no common factors other than positive negative 1. If p over q is a root of p of x equals 0, then p is a factor of the last term and q is a factor of the leading coefficients. In rational zeros theorems, these are also what we call potential zeros. It gives us concepts and specific list of potential zeros. So it's better to understand this theorem with examples. Let's begin with this first example. Consider this polynomial function and find the potential zeros. X to the fourth power minus 3x cubed minus 8x squared plus 12x plus 6. With rational zeros theorems, in listing class the potential zeros, we will just consider the last term, which is your p, and then your first term, which is your q. Well, in this case class, your q here is 1, right? So meaning to say class, you'll just consider here the factors of your p, which is 16. You're going to list first the factors of p, which is 16. And those are positive negative 1 and positive negative 16, positive 2, positive negative 2, positive negative 8, and then positive negative 4. So these are the factors of your p, which is 16. Now let's have your q. Well, we just only have one factor for your q, which is positive and negative 1. Now according to rational zeros theorem, it will be p over q as your potential zeros. I repeat, it's p over q, which means we're going to divide one by one the factors of your p by your q. Since your q here is just 1, meaning to say class, automatically class, your pz or your potential zeros are the p themselves. So your potential zeros are positive negative 1, positive negative 2, then positive negative 4, positive negative 8, and positive negative 16. So what do these PZ mean? We need to say class, these are the numbers that can be factors of the given polynomial function. So that's why we labeled this as your PZ or the potential zeros. Let's have another. Find the potential zeros of 2x cubed minus x squared minus 9x minus 12. Okay, so let's start first with listing the factors of 12, which is your p. Now your p here is negative 12, and then your q here is 2. So meaning to say class, we'll start by listing the factors of 12, and those are positive negative 1, positive negative 2, positive negative 3, positive negative 4, positive negative 6, and positive negative 12. So positive negative 12. So these are the factors of p. Now let's have q. Now your q in the given is 2. So which means the factors of 2 are positive negative 1 and just positive negative 2. Obviously class, we have now coefficient that is not equal to 1 of q, which means which means you're going to divide one by one the numbers in P by the numbers in Q. We begin by listing 1, 2, 3, 4, 6, 12 as your PC, since if we're going to divide this by 1, it will be the numbers themselves. Next, since you're done with Q, you're going to divide again each number in P to the next number, which is 2. So we will have 1 divided by 2 is obviously 1/2. Then 2 divided by 2 is just 1, which is already in the list. So there's no need for us to repeat 1. Then 3 divided by 2 is 3/2. So we list that here. Then 4 divided by 2 is just 2, which is already in the list. 6 divided by 2 is already in the list. Then 12 divided by 2, which is 6, which is also on the list. This is now the complete list of potential zeros. Positive -1, positive -2, positive -3, positive -4, positive -6, positive -6, positive -12, positive -1/2, then positive -3/2. Here's the thing, class. If we do have leading coefficient in polynomial function that is not equal to 1, automatically, class, there are fractions as your PZ. Obviously, class, here, the given has leading coefficient, which is 2. So meaning to say, class, there should be fractions in your PZ. So this is how you get potential zeros. Again, it gives you list of what might be the factors of the given polynomial functions. Now, after having, of course, the list, the second theorem here that we will use in narrowing down the factors are known as lower and upper bounds. Now we say that a real number b is an upper bound for the roots of an equation if every real root is less than or equal to b. Similarly, a real number b is a lower bound if every real number is greater than or equal to b. The following theorem gives us idea, or it narrows down the list. We will have, class, what could be the lower and the upper bound factors of polynomial function. So let's begin, class, by discussing first the theorems. Now let f of x be a polynomial with real coefficients and a positive leading coefficients. Let's begin first with upper bound. Now when f of x is divided by x minus b with b greater than 0 or positive, class, using synthetic division, and if the row contains the quotient and remainder has no negative entry, what does this mean? Meaning to say, class, everything is positive. Then your b here is an upper bound for real zeros of f of x. Next, that's for upper bound. For the lower bound, class, when you divide f of x by x minus a, considering that a is less than 0 or negative, class, using synthetic division, and if the row contains, class, the quotient and the remainder are alternating in sign. Okay, this one is easy to understand. The quotient and the remainder must be alternating in symbol. Okay, regardless if you start with positive or negative, as long as the symbols are alternating, class, then a is the lower bound for real zeros of f of x. Let's have this example. Use Use upper and lower bounds theorem to identify bounds of f of x equals 2x cubed minus 5x squared minus 6x plus 4. Now, of course, by rational zeros theorem, you're going to list the potential zeros of the given f of x. Your p here is 4 and then your q here is 2. So, having this, the potential zeros are positive negative 1, positive negative 2, then positive negative 4, positive negative 1 half, and then positive negative 1/4. So with this class, we will use these numbers by synthetic division, and let's see one by one which of this is the upper bound first. Now, according to the theorem of upper bound, by synthetic division, the quotient and the remainder must be all positive numbers. Okay? So let's have first x minus 1. So we identify first the coefficients of the given, and those are 2, negative 5, negative 6, and 4. Now, by synthetic division, obviously, we will start first with x minus 1. So, your divisor here is positive 1 in leading in synthetic division. So, with this, we'll have 2 times 1 is 2. And then negative 5 plus 2 is 3. Then multiply again. Negative 3 times 1 is negative 3. Then add, it will be negative 9. Then negative 9 times 1 is negative 9. Then 4 plus negative 9 is positive 5. Now looking at the answer, do we have here all positive numbers? No. So what does it mean? Meaning to say, class, your x minus 1 or 1 is not the upper bound. So we'll have, class, the second binomial, which is x minus 2. Using the same given, 2, negative 5, negative 6, 4, let's have synthetic division of x minus 2. Using the same process, bring down the first number. 2 times 2 is 4. Negative 5 plus 4 is negative 1. Negative 1 times 2 is negative 2. Then negative 6 plus negative 2 is negative 8. Then negative 8 times 2 is negative 16. So again, do we have here all positive numbers in our answer? No. So again, what does this mean? What does it mean? Meaning to say, class, your x minus 2 is still not your upper bound. So we'll continue with the rest. With the third, which is x minus 4. Using the same given, class, bring down the first number. It's 2 times 4, it is 8. Then negative 5 plus 8 is positive 3. Then 3 times 4 is 12. Then negative 6 plus 12 is positive 6. Then 6 times 4 is 24. And then 24 plus 4 is 28. Now looking at the answer in synthetic division, everything is positive. So we have now here upper bound, which is positive 4. By the way, in identifying, class, upper bound, it should be, class, positive. Okay? Everything should be positive. You notice here, I did not use the negative in the potential zeros because we're looking for upper bound. And in identifying upper bound, of course, it should be the positive. But in a binomial form, it should be minus x minus 1, x minus 2, and x minus 4. So, the 4 here is your upper bound. Now, let's get now the lower bound of this, and the process of getting, class, the lower bound is the same as the upper bound. However, this time, we'll consider the negative potential zeros. And what we are after here, class, of course, alternating symbol. So with this, we begin by listing again, by writing the given 2, -5, -6, and 4. These are the coefficients of the given. So let's start first with x plus 1. So by x plus 1, your divisor will be -1. So it will be, bring down the first number, 2 times -1 is -2, -5 plus -2 is -7, the -7 plus times -1 is +7, okay? The -6 plus 7 is +1, 1 times -1 is +3. Do we have here alternating symbol? No. So -1 is not the lower bound. We proceed now with the second, which is x plus 2. So by our divisor, it will be -2. So bring down the first number, 2 times -2 is -4. And add negative, it will be -9. The -9 times -2 is +18. Then -6 plus 18 is +12. Then +12 times -20 times -2 is -24. The -4 at 24 plus 4 is -20. Looking at the answer, do we have alternating symbol? Yes. So meaning to say, class, we have now lower bound, which is your -2. Coming up with your answer, the upper bound of the given f of x is 4 and the lower bound is -2. So what do this mean? Meaning to say, class, from our potential zeros, it narrows down that the factors of the given f of x won't have greater than 4 and will not have lower than -2.